Before we look at capacitors or inductors in a circuit, we're actually going to start by briefly looking at capacitor structure. There are a lot of different ways that a capacitor can be structured to have capacitance, but we're going to start with the most basic structure, which is a parallel plate structure. And so as we can see on the left over here, we have these two parallel conducting plates, which in the drawing are shown as being white. Sandwiched in between these two conducting plates is a dielectric layer, which in this figure is shown in blue. This dielectric layer is an insulator that is not going to allow current to flow through it. Now, ultimately, if we're talking about a capacitor, we are interested in the capacitance of the capacitor, the same way that we would be interested in the resistance of a resistor. So in the bottom of the slide, we see an equation for how we can determine capacitance. On the next slide, we're going to go through what each of these terms are, but let me point out a few key things here since we have this drawing on the right. Two of these terms, the area A and the distance D, are related to the geometry of the capacitor. So the area is going to be related to this width times length, so basically the cross-sectional area of the capacitance, and the D is the spacing between the two parallel plates. In other words, the thickness of this dielectric layer. So our units for capacitance are farads, so we'll use F. So again, this is similar to how for resistance we said our resistance had units of ohms, and we used the capital Greek omega. Now, 1 farad is a very large capacitance. Typically, capacitances are going to be in the picofarad to microfarad range. So if you go back and review your SI units and SI prefixes, pico is 10 to the minus 12th. Micro is 10 to the minus 6. Now, of course, we can have smaller or larger, but typically that's what we'll see. So now looking at each of these terms in the equation from our previous slide, so I've just copied that here, we have, in addition to the A and the D, which we mentioned on the previous slide, so A we see as our cross-sectional area of plate overlap, D is the distance between our plates. We also have these two epsilon terms. So the epsilon naught is our permittivity of free space. So here's the value of the permittivity of free space. Oftentimes this is given in farads per meter. It's not uncommon to see this in farads per centimeter as well. And then epsilon r is our relative permittivity. And so this is a material property. So if we have silicon dioxide, that's going to have a different permittivity than a hafnium oxide, for example. So if you look on page 139 of the textbook, there's a table that has some example relative permittivities. So this relative permittivity is going to be dimensionless, and so you can confirm that with a dimension of farads per meter in our permittivity of free space, a cross-sectional area in meters squared, and a distance in meters, that we will get units of farads for our capacitance.